Haven't even said anything yet. Okay. So the title of this talk is Equilibrium Binding Interactions Between Lotrafilcon A Soft Contact Lenses and the two Prostaglandin Anti-Glaucoma Drugs Bimatoprost and Tafluprost. The short title is, if you administer one of these drugs and you're wearing a contact lens, does it matter? The even shorter title is, this is Mark Burns' presentation in reverse. If you came here to understand drug delivery, that's not what this talk is about. It's drug delivery backwards. I'd also like to acknowledge that the support for this project came from Allergan. Especially in this venue, it's important to acknowledge that. One last thing, this will be unlike any other presentation you've seen in the whole conference. This is a physical chemical study. There are no pictures of eyeballs. Don't wait for the last slide. It's just not there. So the overview of the presentation, I'll show you what the drug structures are and what the drug products are. Just a brief slide on what the Lotrafilcon lens is. Unfortunately, there's some math involved in this project, so I have to go over a couple of equations with you. We'll show you how the experiments were done, then the results, and a few conclusions. So the two prostaglandin drugs are Bimatoprost and Tafluprost. You can see the structures below. They're both prostaglandins. They're both glaucoma drugs. Bimatoprost is formulated as 300 mics per mil in a simple aqueous buffer. Tafluprost is 15 mics per mil, then glycerol plus buffer. Log P 3.2, just in case you don't know, if you mix octanol and water, they're immiscible. They make two phases. If you put a solute in that mixture, it partitions between octanol and water. Hydrophobic drugs partition selectively into octanol. P is a ratio of the concentration in octanol to water, so log P of 3 means there's 1,000 times more drug in octanol than in water. That's a hydrophobic drug. Bimatoprost is log P of 3. That means 1,000 times more in octanol. And Tafluprost is log P of 4.5. That means like 50,000 times preference over octanol and water. It's almost impossible to measure a log P that high. Bimatoprost is an Allergan drug, and Tafluprost is sold by a company whose name must not be mentioned. So the Lotrafilcon lens, very popular soft lens. It's a block copolymer, part siloxane, part perfluoroether. It's designed to be highly porous and highly permeable. And the literature teaches that many drugs absorb rapidly into this lens. So the question is, how rapidly and how extensively do the two prostaglandins absorb into this lens? So equations. We define, look, I can't even find my marker there. Where is it? Oh, I got the wrong button. Okay. So E sub B is equilibrium binding constant. It's an equilibrium constant. If we define the mass of solute that ends up in the polymer as M sub P, and the mass of solute that ends up in the solution is M sub S. We use W sub P as the weight of the polymer lens and V sub S as the volume of solution. So E sub B is basically the ratio of M sub P over W sub P divided by the ratio of M sub S over V sub S. It has units of liter or unit volume per unit weight. There are other ways to do that, but the solutions are in volume, the polymers are in weight. It's just experimentally easy to represent that. The other term we want to define is F sub solution. So if I put a milligram per mil of drug in solution, I incubate it in the presence of a contact lens, and 60% of it is left, then F equals 0.6. That's the fraction remaining from the initially added amount that's in solution. And I won't bore you with the algebra, but if you take the reciprocal of 1 over F sub solution, it plots versus W over S, and the slope is E sub B and the intercept is 1. So we vary the volume that we apply to a single lens, and we plot that WV ratio versus 1 over F, and the slope then becomes the equilibrium binding constant. So how do we do this? We take a contact lens, we blot it dry, we weigh it, we cut it into pieces, throw it in a test tube, and we incubate it with drug solution. In this case, the drug solution is the drug product. Obviously, the equilibrium constant is going to depend on the solution constituents. So we use the actual drug product. We vary the solution volume over a range, and we keep the mass of lens constant. We assay for the concentration of drug present in solution after a certain incubation interval by UPLC. Most of the work is done at 37 degrees. We did one experiment at 25. We don't believe it's a good idea to do an experiment like this. It's just a snapshot. What does one drug do under one set of conditions? So we've expanded the scope to include some marker compounds who have known log p-values. A simple homologous series of methyl, ethyl, and propyl esters of phthalic acid, DMP, DEP, DPP, and again a simple homologous series of methyl, ethyl, and propyl esters of p-hydroxybenzoic acid, methylparaben, ethylparaben, and propylparaben. Experiment is done the same way. We dissolve a cocktail of these marker compounds in PBS and incubate them with a lens and assay what's left in solution by UPLC. So this is the worst slide, I promise. The first study was done with dimethylphthalate. We put it in at 300 mics per mil. That's the same concentration as Bimatoprost in its formulation. We measure how much of that is left over at the end of incubation as a function of the volume of solution that's added. So as we add more and more solution, the concentration of drug in solution increases, which is to say that the fraction in solution increases as the volume increases over a contact lens. That's pretty obvious. The next experiment was done the same way, but we kept the solution volume at 0.2 and we varied the time from 0.25 to 0.5 to 1 to 2 hours. And what you'll see is that the fraction in solution is constant from about 15 minutes. That means the absorption is quite rapid. Whatever's going to happen seems to be done in about 15 minutes. A similar experiment is done with diethyl phthalate. Here we varied the solution to volume ratio at 1 hour, and you'll see that again the fraction in solution increases as the volume of solution increases, but you'll notice here that the fraction in solution is much lower than the fraction in solution with dimethyl phthalate. That's because diethyl phthalate is more hydrophobic than dimethyl phthalate, and it partitions preferably into the hydrophobic lens. DPP, dipropyl phthalate, what you'll see is it partitions into the polymer phase even more extensively, and again, all the binding that's occurring seems to be occurring in about 15 minutes. So what about Bimatoprost? This is how we determine the equilibrium binding concentration for Bimatoprost. We have 4 samples, each made up in triplicate. The 4 samples are incubated with various volume to solid ratios. We measure the fraction in solution. We know the weight to volume ratio, and we calculate 1 over F. And we do linear regression of 1 over F versus weight to volume ratio, and we get a slope of 0.2 and an intercept of 1 and an R squared of 0.907. Pretty good, pretty good. With Tafluprost, we did the same experiment. To make a long story short, the slope is about 0.05 and the R squared is about 0.75. The fit to the line isn't as good. That's because with Tafluprost, there's so little of it in solution, it's very hard to measure the concentration. It's down to the quantitation limit of the chromatography method. So there's a little more error associated with Tafluprost than there is for Bimatoprost, but the slope value of about 0.057 is about 3 times higher than the slope value for Bimatoprost, meaning that Tafluprost partitions into the lens phase about 3 times more strongly than Bimatoprost. So here's a graph. This is the reciprocal F subsolution versus the weight to volume ratio for a series of phthalates. The red diamonds are dipropyl phthalate. The little red boxes are diethyl phthalate, and the little blue boxes are dimethyl phthalate. You'll see that the slope for the dimethyl phthalate line is about 0.02. That's about the same number we got for Bimatoprost. So dimethyl phthalate binds into the lens about the same way that Bimatoprost does. You'll see the R squared values are pretty good for dimethyl and diethyl, and the R squared value is not nearly so good for dipropyl. Again, it's an issue of it's so insoluble in water, there's so little to measure, there's just experimental uncertainty around the analytical quantitation of the drug. But you can clearly see the ginormous difference in binding affinities for these 3 solutes. Similarly, for the parabens esters, the top line is for propylparabens, the middle line is for ethylparabens, and the bottom line is for methylparabens. You'll see for methylparabens the slope value is about 0.05. That's the same number more or less we got for tafluprost. So dimethyl phthalate binds into the lens about the same way that tafluprost does. Here you can see the straight lines are quite a lot better. We just didn't have quite so many problems with solubility issues with propyl parabens as we did with some of the other molecules. This experiment, we studied the temperature dependence of tafluprost binding to the lens. We did it at 25 degrees and we did it at 37 degrees. So the red diamonds are 25 degrees. The blue triangles are the experimental points for 37 degrees, and the line is the theoretical line using the equilibrium binding constant. What's interesting about this, what's plotted on the y-axis here is not 1 over f, but f. Okay, so the fraction in solution at 25 degrees is quite a lot higher than the fraction in solution at 37 degrees. That means when you warm it up, it drives the molecule into the polymer. I'm sure there's some interesting thermodynamics behind that, but we didn't explore that. So now I'm plotting the log of the equilibrium binding constant versus log of P. E sub B and P are both equilibrium constants. The logs of those equilibrium constants should be proportional to free energy. So chemists call these linear free energy plots. If we look at the blue plot, that's for the parabens, and you see the 3 parabens molecules. We get an R squared there of about 0.9. So there's a pretty reasonable dependence of binding to log P. For the phthalates, we see another pretty good line. The R squared is about 0.9, but it's a quite different line than the line for the parabens. For the 2 prostaglandins, all I could do is draw a straight line through 2 points, but you'll see that the tafluprost, which is a higher log P, is following the same trend, but clearly all 3 of these molecular classes fall on different lines. So what that means is that yes, hydrophobicity is important in controlling the binding of these drugs to these lens materials, but it's obviously not the only controlling factor. Hydrogen bonding, other kinds of interactions, we didn't have the opportunity to probe, other mechanisms. So in conclusion, the fraction of either bimatoprost or tafluprost that binds to the lens increases with the increasing lens to solution ratio. The more lens you've got, the more that goes into the lens. Both drugs partition very rapidly and very extensively into the Lotrafilcon A lens. But what about the case of a contact lens wearer with a single lens and 2 eye drops, 60 microliters? Well, we can't do that experimentally very well, but armed with the equilibrium binding coefficient, we can calculate what that amount is. What we calculate is that only 16% of initially added bimatoprost would be in solution. The rest would be in the lens. With tafluprost, which binds even more, it's about 3 times less, about 6% is present in solution. So I'm a contact lens wearer, I put in my eye drop, 15 minutes later, it's pretty much all in the lens. What does that mean in the clinic? We don't know about release rates, we didn't study that. What do we know about efficacy? We didn't study that. At this point in time, not knowing any of those things, it might be prudent to advise wearers not to put their lenses in when they're administering their eye drops. We learned that hydrophobic interactions are important, but not the only significant factor in drug binding to Lotrafilcon A. And that's my presentation. So thank you.
Questions? Yes. Kenley.
So does this mean that, given that it is likely to be an equilibrium process, does this mean that there could be an additional benefit that all that people are struggling to do of holding the drugs in place, you might achieve by simply this equilibrium partition? So eventually when there is no drug in solution, you will get the drug to come out and maybe help?
So imagine a situation where instead of soaking your lens in night in saline, you soaked them overnight in 30 micrograms per mil of bimatoprost in saline. Put the lens in your eye, depending on the volume of solution that you have, most of that drug is now in the lens. What happens when you put it in your eye? Well, at some point it's going to release. We have not studied the release profile from the lens, but that's why I say it's drug delivery in reverse. You heard a talk earlier this morning about people have failed to achieve sustained release of drugs by drug loading into contact lenses. I'm not sure this is necessarily a sustained release issue. This is a convenience issue. Instead of applying an eye drop, missing it half the time, blinking it out, you'd have the drug in that contact lens, and over some period of time, it has to release. The details of that we haven't studied. We don't know.
I noticed that Mark's not here, but Mark would say, but if you absorb the drug in the lens, it's going to be cloudy. So I don't know if you can answer that or not.
Well, I've got 15 micrograms per milliliter of Tafluprost in a solution. I'm going to go out on a limb and say that amount of drug is not going to cloud up a lens. We're not talking about a percent of antibiotic.
Okay. My question actually is, you've done your experiment ex vitro, but you're competing now with tissue for capturing the drug. So it's going to partition differently, won't it, in vivo?
Right. I mean, it's going to partition into the tear fluid. It's going to partition into the cornea.
Yep.
We haven't studied it. We don't know which way that's going to go.
Okay.
If you wanted to do that study, the easy way to do it is you just incubate a lens with solution, and you'll know how much is in the lens, and you can do this experiment. But that wasn't in the scope of our effort.
Last question.
Yeah, you only tried the prostaglandin, which is very hydrophobic. Did you look at the other brimonidine type polar compounds, other hydroxyl bearing compounds, polar molecules? They are also absorbed or observed onto the
So we did not look at them,
lens?
but we learned that hydrophobicity is a strong controlling factor, and we would predict that more hydrophilic drugs will partition less into the lenses, into these lenses.
Okay. So these will be mostly for hydrophobic drugs?
Well, it depends on what you're trying to achieve. What if 50% of a hydrophilic drug partitioned into the lens, and that was enough to get some activity? I mean, it's a complicated question, but clearly the more hydrophobic drugs are going to load up the lens proportionately more.
And the more it loads up, it will give you release over a longer period of time. So if you are putting polar groups like timolol or brimonidine and all that, they will not go that far.
Yeah, we're not calling this a drug delivery device. Okay? We're just presenting an experimental method for understanding what the equilibrium constant is, for understanding what the controlling factors are. The experiment we did where we measured the time dependence of absorption is an easy enough experiment to do to measure the time dependence of release in whatever fluid you're looking for. I think the value in our approach is that we understand the math. We have an experimental setup that's real easy to use. You can do these things in cocktails, right? We understand some of the controlling factors. We've done studies like this many, many times back in my Baxter days, looking at drug interactions with films that are used to make IV bags. And we found there that a combination of hydrogen binding and log P very accurately predicted the extent of binding between a wide range of drugs and multiple polymer materials. I think that's kind of a general phenomenon. We couldn't measure hydrogen bonding for the prostaglandin drugs because that experiment requires using hexane as a solvent, and they're not soluble in hexane. So I couldn't do that experiment with these two drugs.
All right, let's thank Dr. Kenley again.